Welcome to the deep dive. Imagine trying to build a modern skyscraper, but you don't have any blueprints.
Or zoning laws, for that matter.
Right, exactly. No zoning laws, no standardized bricks. You just have, like, 100 workers throwing steel and concrete into a pile.
Just kind of hoping it doesn't collapse on itself.
Yeah, hoping for the best. And that is basically what computer programming was like in the 1960s. It was an absolute chaotic Wild West.
It really was.
Today, we're opening up the Wikipedia biography of the pioneer who actually tamed that frontier. Her name is Barbara Liskov. She was born Barbara Jane Huberman in 1939.
And, if you use anything built with Java or C++S or C#,
Which is, like, everything.
Literally everything. If you interact with the modern digital world at all, you are relying on her brain. We're looking at a fundamental shift in the philosophy of computing today.
Because she didn't just write a few clever programs, right?
No, not at all. Liskov possessed this unique, almost architectural ability. She could look at these overwhelming, tangled, messy systems and just extract an elegant, logical structure from them.
Which was desperately needed.
Desperately. Our mission today is to explore how she changed the very nature of writing software, taking it from this unpredictable craft to a disciplined, rigorous science.
So, to understand how she fundamentally revolutionized coding, I think we have to start with how she fell into it in the first place. Because it wasn't a straight path.
No, it was actually a total accident.
Right, so let's roll back to 1961. She earns her bachelor's degree in mathematics with a minor in physics at UC Berkeley.
And it's worth noting she had only one other female classmate in her major.
Wow, just one.
Yeah, the landscape for women in STEM at that time was, well, incredibly restrictive, so she graduates, and she decides she wants to pursue graduate school for mathematics.
Makes sense.
Right. She applies to Berkeley and Princeton. Berkeley accepted her, but Princeton flat out rejected her.
And the reason why is just wild to read today.
It is. The stated reason, they didn't hide it, was simply that Princeton did not accept female students into their mathematics program, period.
It's just a stark reminder of the era. But looking at her life from a macro perspective, I want to pose a what-if scenario for you listening.
Okay, let's hear it.
What if Princeton hadn't been closed to women? I mean, she probably would have gone there.
Oh, almost certainly.
And she likely would have remained in pure mathematics, dealing with, abstract theories on paper for her entire career. Instead, this rejection acts as this incredible, fortunate detour.
A massively fortunate detour for the rest of us. It pushed her out of academia temporarily and into the commercial sector.
So she moves to Boston, right?
Yeah, she moved to Boston and took a job at the Iron Air Corporation. And that is where she encountered a computer for the very first time.
Which is crazy to think about. She already had a math degree and had never touched a computer.
Exactly. So she discovers programming, works there for about a year, and then takes a job at Harvard working on computer language translation.
So a closed door in pure math literally pushes her into this nascent, exploding field of computer science right at the moment it's being born.
Right. And once she found that field, she clearly recognized her calling because she accelerated so rapidly.
Yeah, she applies to graduate school again, this time Berkeley, Stanford, and Harvard. She chooses Stanford.
And in March 1968, she becomes one of the very first women in the United States to earn a PhD from a computer science department.
That's a huge milestone.
It's massive. And while she was at Stanford, she worked alongside a giant in the field, John McCarthy.
The AI guy.
Yes, he's widely considered one of the founding fathers of artificial intelligence. And her PhD thesis under him was a computer program designed to play chess endgames.
Okay, and to make this work, she developed a mechanism known as the killer heuristic.
Yes, the killer heuristic.
Which, let's break that down for the listener, because killer heuristic sounds like a 1980s slasher film.
It really does.
What exactly is a heuristic in the context of, a 1960s chess-playing computer?
Basically, a heuristic is a problem-solving shortcut. So think about a chess endgame. If a computer tries to calculate every single possible move,
right,
and then every possible response to that move and every response to that response, well, you get the age.
The decision tree just branches out into billions of possibilities.
Exactly. And a 1960s computer would just freeze. It would be calculating until the end of time.
So it needs a way to basically ignore the useless move.
Exactly that. It needs a rule to prune the tree. So the killer heuristic is a strategy where the computer identifies the specific moves that immediately invalidate an opponent's threat.
The killer moves.
Right, the killer moves. And once it finds a killer move, it stops calculating all the other trivial, weaker variations.
Oh, that's smart.
It's brilliant. By developing this, Liskov proved she could tame massive, branching, complex logic. She figured out how to make a machine focus only on what actually matters.
And that ability to isolate what matters is kind of the perfect bridge to the next phase of her career, isn't it?
Absolutely. It's the theme of her whole life.
So she graduates from Stanford, heads back to Mitery as a research staff member. She leads this project called the Venus Operating System, which was a low-cost time-sharing system.
Right.
But as she's working on this, and eventually moving over to MIT as a professor in the 1970s, she spots this looming catastrophe in the tech world.
The software crisis.
Yeah. Hardware was getting faster and cheaper, but the software was turning into a tangled, unreliable mess.
The industry was hitting a total wall. Because computers could suddenly hold more memory, programmers were writing much larger programs. But they were still writing them the old-fashioned way.
Just dumping everything into one pile.
Literally. Just dumping all the instructions into one massive, interconnected, linear pile.
The dreaded spaghetti code.
Yes. In spaghetti code, everything touches everything else. So imagine you have a global variable, a piece of data that any part of the program can see and modify.
Okay.
If you write a piece of code to manage, say, the office printer, and you accidentally use the same variable name that the payroll calculator is using, yeah, the printer code might overwrite the payroll data. You change a line of code in one file, and something completely unrelated mysteriously breaks in another room.
That sounds like a nightmare. So how does she solve this? The sources point to her time at MIT in the 1970s, where she developed a brand new programming language called CLU.
CLU, yes.
Right. And through CLU, she introduced a concept called abstract data types and the principle of data abstraction.
And this is arguably one of the most vital concepts in all of modern software.
Really?
Without a doubt. Data abstraction is the idea that you bundle the data and the operations that manipulate that data into a single closed capsule.
Yeah.
And you hide all the messy inner workings of that capsule from the rest of the program.
Let's put this into a real-world context for you listening. Think about just the basic act of driving a car. When you sit in the driver's seat to go to the grocery store, you don't need to understand the thermodynamics of an internal combustion engine, right?
Thankfully, no.
You don't need to know how the fuel injectors are timed or how the transmission gears align. All you need to know is the interface. You press the gas pedal and the car goes forward.
That is the perfect visualization. Liskov basically looked at computer programming and realized it needed gas pedals.
I love that.
She argued that a programmer should be able to use a block of code, say, a function that sorts a list of names, without having to understand the thousands of lines of logic churning underneath it.
Right. The rest of the program only gets to interact with that capsule through a clean, strictly defined interface.
Exactly. It's essentially hiding the complexities so the human brain doesn't short circuit.
Because we have limits.
Massive limits. We have to consider human cognitive limits. A person can only really hold a handful of abstract ideas in their working memory at any given time.
Yeah, maybe like 7 things at once.
Exactly. So without data abstraction, building something as massive as a global banking network or a modern smartphone operating system, it would be biologically impossible for human programmers.
We simply cannot hold millions of lines of interconnected code in our heads.
No one can. So by creating these abstraction boundaries, she allowed programmers to compartmentalize.
You build one piece, you test it, you make sure its gas pedal works,
Right.
and then you completely forget about its internal mechanics. You just use it to build the next thing.
And that philosophy shifted everything. Her design of CLU directly influenced the architecture of some of the most famous programming languages on Earth. Java, C++, C#, Ada.
Wow.
Yeah, they are all fundamentally built on Liskov's foundation of data abstraction.
Okay, so we've established standard encapsulated building blocks. We have our bricks and our standardized pipes.
Yes.
But if I'm building a system out of a million abstract blocks, the next logical hurdle is making sure those blocks actually play nicely together when I start swapping them out.
Naturally.
Which brings us to her work in object-oriented programming and arguably her most famous contribution, the Liskov substitution principle, or LSP.
Right. She formulated this principle alongside Jeanette Wing in a 1994 paper. In academic terms, it is a formal criterion for subtype correctness in object-oriented design.
That's a mouthful.
It is. It provides a mathematical framework to reason about behavioral compatibility within computer programs.
Okay, hold on. Behavioral compatibility sounds exactly like a term from couples therapy.
It kind of does.
Like, I'm sorry, we just don't have subtype correctness. We aren't behaviorally compatible anymore.
I think a lot of programmers feel that way about their code, honestly.
I bet. But if I'm a developer building an app, what does subtyping and substitution actually look like in plain English?
Let's build on your machinery analogy to clear that up. Imagine you order a standard coffee maker for your office break room.
Okay, simple enough.
The behavioral promise of that machine is very straightforward. You put water and coffee grounds in, and it gives you hot coffee.
Right.
Now, let's say a year later you want to upgrade. You swap out that generic coffee maker for a highly specialized, top-of-the-line espresso machine.
Nice upgrade.
In object-oriented programming, that fancy espresso machine is a subtype of the original generic coffee maker.
Got it. So it's a more specific version of the parent object.
Exactly. Now, the Liskov substitution principle dictates a very strict rule for this upgrade. If you substitute the new, specialized part into the system, it must still fulfill all the basic promises of the original part without breaking the broader system.
Okay, so it still have to make coffee.
Right. The new espresso machine might brew faster, it might froth milk, it might have a digital display, but if this new machine suddenly requires you to, say, connect it to a Wi-Fi network and download a firmware update just to boil water.
Which happens all the time now.
Right. If it does that, it has violated the original behavioral promise.
Because the original promise was just water and grounds equal coffee.
Exactly. It lacks behavioral compatibility. If a system is expecting the simple behavior of the parent object, and the child object throws a completely unexpected demand or error into the mix, the entire software system crashes.
So LSP is basically a do no harm rule for software upgrades.
That's a great way to put it.
It ensures that when you add new complex features, you don't break the promises made by the older features.
And consider the scale of why this is necessary. Modern software isn't written once and shipped on a floppy disk to sit unchanged forever.
Not anymore.
It is an evolving organism. Apps and operating systems are upgraded continuously over decades by thousands of different programmers who have never even met each other.
Right, Sun in 2026 is touching code from 2016.
Exactly. The Liskov substitution principle provides the guardrails that allow that programmer to safely swap a new feature into the old code, confident that the foundation won't crack.
It's brilliant. It really is.
Yeah.
So we've solved the problem of making code comprehensible within a single program. And we've solved the problem of making sure parts can be upgraded without breaking the system.
Yes.
But we are talking about Barbara Liskov, so she doesn't stop there. What happens when these highly organized, abstract blocks of code aren't sitting on just one computer? What happens when a computer in New York needs to talk to a completely different computer in Tokyo? Do her rules still apply?
That is the exact question she pivoted to next. As we moved from single machines to global networks, she began tackling distributed computing.
Which was huge in the 80s.
Right. In the 1980s, Liskov developed a language called Argus. And Argus was the very first high-level language designed specifically to support the implementation of distributed programs.
Okay.
And within that, she demonstrated an incredibly important technique called promise pipelining.
Our sources highlight promise pipelining, but I think we need to visualize how that actually functions across a network.
Sure. Think about ordering food at like a busy, fast casual restaurant.
Okay.
If you place your order and then stand frozen at the register waiting for your burger to be cooked, you are blocking the line.
Yeah, everyone behind me is getting mad. Nothing else can happen.
Right. And in early networking, computers did something similar. One computer would ask another for data, and it would just freeze, completely locked up, waiting for the response.
Which is terribly inefficient if the network is slow.
Tremendously inefficient. So promise pipelining is like the restaurant handing you a vibrating pager.
Oh, I see.
You place your request, the other computer hands you a promise that the result will be delivered later, and your computer can immediately go back to doing other useful work.
It doesn't have to wait around.
Exactly. When the data is finally ready, the pager buzzes and you collect your result.
It allows the whole system to keep flowing asynchronously.
That is so smart. And she didn't just stop with the communication aspect, right? She also developed something called Thor.
Yes, Thor.
Which the Wikipedia bio describes as an object-oriented database system. But alongside that, she focused her research heavily on a concept called Byzantine fault tolerance. Now, I have to say, that is a fantastic phrase.
It's one of the most fascinating concepts in computer science. Byzantine fault tolerance is basically the ability of a distributed computer network to survive and reach a consensus even when some of its parts fail, shut down, or act maliciously. Wait, maliciously. So we're not just talking about a server in London losing power, but a server actively lying to the rest of the network.
Yes, actively sending bad data. The name comes from a famous logical dilemma called the Byzantine generals problem.
Okay, let's hear it.
Imagine an ancient city under siege by several divisions of the Byzantine army. The generals of these divisions are camped on different hills surrounding the city.
Got the picture.
Now, to win, they must all attack at the exact same time. If only a few attack, they will be slaughtered.
So they absolutely need to coordinate a specific time.
Right. But they can only communicate by sending human messengers through the valley, which is controlled by the enemy.
So a messenger might be captured and the message lost.
Exactly. But even worse, one of the generals might actually be a traitor.
Oh, wow.
And he intentionally sends out messengers telling half the army to attack at dawn and the other half to retreat.
So how do the loyal generals figure out the truth if they know the information network is compromised?
That is the core of Byzantine fault tolerance. How do decentralized computers, say, a global network verifying financial transactions, how do they agree on the true state of the ledger when some of the computers might be sending corrupted or contradictory data?
That is basically the foundation of modern crypto and blockchain, isn't it?
It is. Liskov's work provided the mathematical frameworks and algorithms that allow these networks to verify the truth and keep functioning despite chaos, delays, and bad actors.
And if you look at the timeline of all this, it's astonishing.
It really is.
She was solving massive problems for distributed computing, asynchronous databases, and fault tolerance in the 1980s. She was essentially anticipating the architecture and the vulnerabilities of the modern internet decades before those concepts were a reality for the general public.
Her foresight is staggering. She was building the scaffolding for the 21st century before most people even had a personal computer in their homes.
And the scientific community certainly recognized the magnitude of her contributions. I mean, the sheer weight of her accolades is a testament to that.
Oh, absolutely.
In 2004, she was awarded the I.E. John von Neumann Medal for fundamental contributions to programming languages and distributed systems. And then, in 2008, she received the ACM-AM Turing Award.
Which is vital context for our listeners. The Turing Award is universally recognized as the Nobel Prize of Computer Science.
Doesn't get higher than that.
No, it is the absolute highest distinction in the field. And Liskov was only the second woman in history to receive it.
And what's really telling is what the Turing Committee cited when they gave it to her. They specifically highlighted her work on data abstraction, fault tolerance, and distributed computing.
It was a total validation of her overarching philosophy. They weren't just awarding her for one clever algorithm, you know?
Right.
They were recognizing that her specific way of structuring systems had become the default method for the entire global software industry.
The recognition doesn't stop there either. In 2012, she was inducted into the National Inventors Hall of Fame. In 2023, she received the Benjamin Franklin Medal from the Franklin Institute, specifically noting how she enabled the creation of reliable, reusable programs.
The list really just goes on and on.
She's a member of the National Academy of Engineering, the National Academy of Sciences, and sources point out she built this unparalleled legacy while maintaining a full life outside the laboratory, too.
Yes, the biography notes she is Jewish, and she married Nathan Liskov in 1970. They built a family together, and they have a son, Moses Liskov.
And Moses actually followed directly in his mother's footsteps.
He did.
He earned his own PhD in computer science from MIT in 2004 and now teaches computer science at the College of William and Mary. It's just an incredible family legacy in the discipline.
It really is. And she is still active at MIT, serving as an institute professor and Ford Professor Engineering, leading the programming methodology group.
When you zoom out and look at her trajectory, it's this profound narrative of human ingenuity organizing raw chaos.
That's exactly what it is.
We started this deep dive talking about a young woman in 1961 sitting in a math class at Berkeley with only one other female student, a woman who was handed a rejection letter from Princeton purely because of her gender. And from that closed door, she found a chaotic, lawless frontier of punch cards and tangled wires. She stepped into that digital Wild West and said, "We are not just going to hack things together. We're going to build a disciplined, reliable city."
Yeah.
Through data abstraction, she gave us the standard building blocks. Through the Liskov substitution principle, she gave us the zoning laws for how those blocks connect. And through her distributed computing work, she taught those cities how to talk to each other safely across the world.
She provided the very rules that allow the human mind to comprehend and build digital structures far larger than our brains were ever evolved to handle natively.
Which is an incredible gift.
It is. But reviewing her life's work today actually raises a critical, forward-looking question for you, listener.
Oh, I like where this is going.
Well, Liskov dedicated her life to creating frameworks like abstraction boundaries and behavioral substitution rules designed specifically to make complex code understandable and predictable for human programmers.
Because we have those severe cognitive limits we talked about.
Precisely. But today, we are rapidly moving into an era where artificial intelligence is beginning to write vast amounts of our software.
Right.
AI does not share our human cognitive limits. An AI can hold millions of lines of spaghetti code in its memory without short-circuiting.
Wow, that's a really good point.
So as we increasingly hand over the drafting of our digital blueprints to machines, the question is, how will we maintain Liskov's foundational principles of reliability and behavioral compatibility when humans are no longer the ones doing the abstracting?
Will the AI even care about our rules?
Exactly. Will we enforce the city codes she gave us? Or will we let the machines drag us right back into a new, totally incomprehensible Wild West?
That is a phenomenal question to leave on. As the architects change, do the blueprints survive? Definitely something to mull over the next time you press a digital gas pedal and expect the car to simply move forward. Thanks for joining us on this deep dive. We'll catch you in the next one.